Any questions on what we did last week, quantum algorithms, quantum complexity? Nope. OK. This week is a bit of a grab bag of other topics. Today and tomorrow, I will be doing quantum error correction. And then later in the week, in some order yet to be determined, there will be quantum cryptography and quantum information theory. So quantum error correction is probably going to be very important in building a quantum computer because, well, for a couple of reasons. So first of all, we're building a quantum computer out of very small things, right? Single atoms or small superconducting loops or something like that. And small things are, of course, going to be more susceptible to any kind of disturbance than bigger things. And even as classical computers, the feature size gets smaller and smaller. They have to worry more and more about errors. But the other thing, of course, is that quantum information is inherently much more susceptible to noise than classical information because looking at a quantum state, measuring it will decohere it, destroying the superposition that we depend on to make quantum algorithms work. And it doesn't have to be a person, of course, that's looking at it. It can be anything that's nearby, the environment, a single atom that's not supposed to be there but is somehow interacting with your system can cause that decoherence. So we expect that to build quantum computers, we need some way of getting rid of these errors once they occur. And so that's where quantum error correction comes in. Now, today, I'm just going to focus on the pure quantum error correction scenario, which is a communication scenario. So we have Alice trying to send a message to Bob. Instead of an eavesdropper this time, we have a noisy channel. Alice has a perfect quantum computer. Bob has a perfect quantum computer. So the only errors that occur are in transmission. Now, I should say that while I phrase this as a communication scenario, you can also think of it as a memory scenario, right, where Alice has a perfect quantum computer, but then she wants to create a quantum state and store it for some long amount of time. And during that time, there could be errors that occur while she's storing it. And then at the end, she comes back. And so in this case, Bob is Alice's future self. She comes back and wants to decode it and do whatever it is that she was interested in with the state. Right. And so obviously, the idea that Alice and Bob have perfect quantum computers is a big simplification here. And tomorrow, I will talk briefly about fault-tolerant quantum computation, which is what you can do to actually make a quantum computer when the gates are noisy. So the idea there is you have a quantum error correcting code, and you put on top of it some additional procedures that let you do gates on qubits while they're encoded and protected against errors. So anyway, so how are we going to deal with this? Well, the basic idea of an error correcting code or quantum error correcting code is that you're going to add extra qubits, and that adds some redundancy that you can use to protect against errors. So to get an inspiration of how to do that, let's focus on first talk about classical error correction. So how does classical error correction work? What's the very simplest thing you can do? That's the repetition code. So Alice, in this case, wants to just send a single bit to Bob. And so she's going to have either 0, 1, and she's going to encode 0 as 3 zeros and a 1 as 3 ones. OK? Then she sends those 3 bits over this noisy channel. And then Bob will receive something, which might not be exactly what Alice sent. So suppose Bob receives something like 0, 1, 0. What's he going to do with that? Well, maybe he'll say, OK, there's 2 zeros and 1, 1. So I'll assume that the original message that got sent was 0, 0, 0. So he corrects that back to 0. The basic rule there is Bob is just going to look at these 3 bits and take the majority, right? So whichever one is most common. Obviously, if all 3 are the same, then he doesn't have problems. But if they disagree, go with the one that's more common. And so the justification behind this is you can think of a of an error model for the channel. You say, well, suppose this channel is treating each of those bits independently. And each bit has an error, is flipped, with probability p. Okay? So in the case that so it is possible, of course, that there were actually two errors here, right? And that the state started as 1, 1, 1. There were errors on the first and third bits, and then what Bob is correcting is the wrong thing. But in order for that to happen, there need to be two errors, right? If there's one error, Bob will deduce correctly what the original state was. And so we have one error that occurs with probability O of p, and two or more errors, could be three errors, of course, with probability O of p squared. Okay? So in this case, he's right, and in this case, he's wrong. And of course, if there's no errors, he's also right. Okay, so the point is that with the error-correcting code, Bob's probability that his decoded bit is wrong is order p squared. Whereas for an unencoded message, then there's probability p of being wrong. Okay, so I mean there is a constant factor here, roughly 3. But if p is small enough, less than about a third, that means that that Alice and Bob win by using the error-correcting code. Okay, if p is too large, the probability of error is too large, then the fact that there's more errors that can occur by adding extra bits means that they're not actually winning by using the error-correcting code. They're better off, just taking their chances with the unencoded bit. But generally, we're going to think about situations where the error rate is small, and therefore the code is useful. And in particular, rather than run through this whole argument every time, we can just say, oh, well, look, the probability of two errors is always going to be order p squared. So we're going to, if we can come up with a code that corrects arbitrary single qubit errors, then we know that we're improving things when p is small. Okay? And more generally, if we want a code that corrects t errors, then the probability of logical error after decoding is O of p to the t plus 1. But what we're going to do mostly is we're just going to say, oh, let's come up with a code that corrects t errors, and then not worry about the case that happens when there's more errors, because that's unlikely. Okay? Any questions?
When p is really large, it's slightly more complicated than order p squared, right? It's order p squared.
Yeah, well, right. So this is O of so this is 3p times 1 minus p squared, and this is 3p squared times 1 minus p. That's right. Plus the 3 error thing, which is p cubed. Other questions? Okay, so now let's move on to quantum error correction. Oh yeah.
So for error correcting codes, if you have more encoded bits, there are more efficient methods.
That's right. Yeah.
So depending on the situation, is there an analogous situation in quantum computing where
sure.
Depending on how many things you want to encode, we can
Yeah, absolutely. I'm not going to be talking a whole lot about that, but yeah, I mean, so for classical error correction, basically, I mean, so this repetition code actually is quite a good code if what you're concerned about is correcting a high probability of error. And so in general, there's some trade-off where you can encode many bits at once. But then maybe you're not, even if it's kind of optimal code, it's not going to be as good at correcting high error rate. So there's a trade-off between correcting error rate and the amount of overhead, the extra bits that you need. And the same thing happens in quantum error correction. But as you'll see, it's a worse trade-off. OK. So then let's move on to quantum error correcting code. So the first thing you might think to do is let's just imitate the classical repetition code and make a quantum repetition code. OK? So we'll take a state psi and encode it as 3 copies of psi. OK? So how does that sound? Problematic, right? There's the no cloning theorem, right, which tells us that that's not a possible thing to do. And indeed, as you think about quantum error correction more closely, you'll come up with a bunch of other problems that seem like they argue against the possibility of quantum error correction. So what are those problems? So the first one is the no cloning theorem. So the other thing is, remember when I said in error correction, Bob should look at these 3 bits and take the majority. Okay, that's also going to be a problem with quantum error correction because you don't want to look at the bits because that'll destroy the superposition, right? You want there to be a superposition. So we have to be somehow very careful of that. Qubits to OK. So what else? Well, there's also many more errors that can occur on a quantum state, right? So there's bit flip errors, but also, which is what happens classically. But we also need to correct phase errors. And in fact, there's really, when you get right down to it, there's actually an infinite set of errors that can occur, right? Because you also have coherent rotations, decoherence, and things like that. This seems like a daunting list of problems. And at this point, you might say, well, it seems hopeless. But of course, it isn't hopeless, because I just told you I'm giving 2 lectures on quantum error correction. But let's not try to solve all of these problems at once. Okay, let's start at the beginning and see what we can do from there. So the first problem about the no cloning theorem, actually that's something we discussed a little bit in the first week, how to deal with this, right? Which is that you can't repeat an arbitrary quantum state. You can't take alpha 0 plus beta 1 and make it alpha 0 plus beta 1 tensor alpha 0 plus beta 1. But you can repeat in a given basis. Okay? So let's not worry about the other kinds of errors and just think about a code to correct bit flip errors, right? We have a code that does this classically, which is the repetition code, and of course lots of others. So let's try to make a quantum version of that code to protect quantum bits against bit flip errors. Okay? And we know that the basis states, the logical 0 and the logical 1, are protected by the repetition code. So why can't we just protect superpositions in the same way? And we get around the no cloning theorem, remember, because we're only copying in one basis, right? So we want a code that takes alpha 0 plus beta 1 to alpha 0, 0, 0 plus beta 1, 1, 1. Okay? And that's allowed by the no cloning theorem. And we know that if there's a bit flip error, well, and we look at the state, we can figure out which qubit it occurred on and correct it. Okay, so that part is good. But looking at the state is not good. Okay, so that's the problem too. So how do we deal with that? Well, so let's see exactly what does happen when we have a bit flip error. Suppose we have, bit flip error on qubit 2 here. Let's call this psi. Bit flip error on qubit 2 will give us alpha 0, 1, 0 plus beta 1, 0, 1. Okay, so clearly if we measure each of these 3 qubits, it'll collapse the superposition, and the logical state is then gone, or at least the superposition part of it is gone. But you'll notice that there is some property that's shared by both of these 2 qubits, which is that the middle bit is different from the first and third. Right? So if we can measure that property and say, oh, the middle bit is different from the other 2 bits, but nothing else, it's the only thing we want to measure, that won't collapse the superposition, right? Because that's something that's true if we have this, if we have this, or if we have the superposition. It's still true. Okay? So how do we do that? Yeah?
Sorry, this is a little bit off topic, but I was wondering what error correcting would look like, even in classical case, if we have more than binary bits.
Yeah, it looks pretty similar. I mean, it's a long story to tell the details, but like the repetition code, you can just make it the same, right? Because you can then encode a DIT, right? So say you have 5 states, 0, 1, 2, 3, 4. Well, 0 gets encoded as 3 zeros, and 1 gets encoded as 3 ones, and 4 gets encoded as 3 fours. Okay, that's the easiest way to do it. Okay, so back to this. So we want to identify that the second qubit is different from the first and third without learning anything else about the state. So how do we do that? Well, actually, we can learn a little bit more. We can break it down into 2 pieces. We can say, are the first 2 bits the same or different? And are the second 2 bits the same or different? Okay, so let me write down a circuit that does that. So here's the code state. So it should be, should be something of this form with possibly an error on it. And then we're going to add 2 ancilla qubits. So this started in state 0. And to see if the first 2 qubits are the same or different, we're going to do 2 C0 gates. So from the first qubit and the second qubit to this first ancilla. Okay, and you see that if both of them are 0, neither of these C0s fires, this comes out 0. If both of them are 1, then both C0s fire, and this also comes out 0. Okay, but if one of them is 1 and one of them is 0, then this qubit comes out 1. So this is indeed detecting whether these 2 things are the same or different in the computational basis. Okay, and similarly, we can do C0s from the second and third qubits to the second ancilla to see whether the second and third qubits are the same or different. Okay, and so then these 2 qubits we measure, and this gives something called the error synchrome. Okay, so the error synchrome in this case is just 2 bits, and it's supposed to tell us what the error is. So let's think of the possibilities. So 2 bits, so there's 4 possible values. So suppose we see 0, 0 here, right? So what does that mean? That means the first 2 bits are the same, and the second and third bits are the same. So all 3 bits are the same. So that means that there's no error. Or maybe there were 3 errors, but we're not hoping to correct that, right? We're just focusing on the case where there's 0 or 1 error. Okay. Now suppose we see the error synchrome 0, 1. So that means the first 2 bits are the same, and the second and third bits are different. So what does that tell us about the error? It's the third bit, right? Because the first 2 are the same, so either one of them or both of them would have to be flipped in order for that to be true. But the third bit, that can explain this. And similarly, if we have error syndrome 1, 0, that means the first two are different, but the second and third are the same. So it must be the first one that's flipped. Here. And if we have 1, 1, well, that's the case we saw up here, where the first two were different and the second and third were different. And so that's the second qubit that got flipped. Okay? So in this particular case, there's 3 possible bit flip errors that could occur. And we can identify them by looking at this error syndrome, or see if there's no error at all. Here. And the thing to note here is that we measure this error syndrome, but we didn't learn anything at all about the encoded state. Right? We have no idea from this error syndrome whether the logical state was 0 or 1 or some superposition. Okay? So this thing is identifying the error without learning anything about the encoded state, and that's OK. That will not destroy our logical superposition. So this really is a quantum error correcting code, albeit one that only corrects bit flip errors, which is certainly not the most general thing that can happen. OK? So we solved problems 1 and 2 here. OK? So that's good progress. So now let's start to work on problem 3. Well, before we do that, let me see if there's questions about this. Nope. OK. So now let's work on problem 3. Oh, yeah.
Once you've gotten back to the 0, 0, 0, 1, 1, 1, how do you collapse them back down to like just a
Right. So yeah, OK. So I didn't show you the encoding circuit, the decoding circuit here. But it's very easy. So OK, first of all, the first thing you probably want to do is you say, well, there's an error. So let's say it was on the third qubit. Let me do a bit flip on the third qubit to get back. OK, so now I have something of this form again. So the encoding circuit was pretty easy, right? Because we started with a state which is alpha 0 plus beta 1. We're adding 2 extra qubits. And then we can just do C naughts to make them the same. OK? So that's the encoding. And the decoding is the same thing backwards. OK, so moving on. So let's try to come up with a code that corrects phase errors. And maybe let's start by doing a code that corrects only phase errors, but not bit flip errors. OK? So one thing we can notice is that if you look at the Hadamard transform, it takes us between the computational basis, the 0, 1 basis, and the plus and minus basis. And in this plus-minus basis, the phase error, Z, acts like a bit flip error. Right? Because a Z on the plus state gives us 0, minus 1. So it gives us minus. And a Z on the minus state gives us plus. So it flips us between those two possibilities. And actually, it's also true that in this basis, X acts like Z. Because what does bit flip do? Well, take 0 plus 1 to 1 plus 0. So plus goes to plus. And 0 minus 1 goes to 1 minus 0, which is minus, minus. OK? So X now gives the phase shift, and Z does the bit flip. And so what that means, this is the part that's important here, because it means that we can use the same bit flip correcting code that we used before, just do it in the Hadamard rotated basis, the plus-minus basis instead. OK, so here's a phase error correcting code. We'll take 0 and encode it as plus, plus, plus. And 1 and encode it as minus, minus, minus. And of course, alpha 0 plus beta 1 gets encoded as alpha, well, save some on the kets, plus, 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 plus beta minus, minus, minus. Okay? And if we have a phase flip, well, then one of these three things will be, one of these three qubits will be the same, will be different from the other two, right? So just by trying to tell in the plus minus basis whether they're the same or different, in the same way as we did before, we can correct that phase error. Okay? And in particular, we can use the same circuit, but with Hadamard's everywhere to switch the basis. Okay? And of course, I showed you in the first week that if you do Hadamard's on the C0, that gives a C0 in the opposite direction. So the circuit that comes out looks basically the same, but now the C0's in the opposite direction, and the ancillas have Hadamard's on them. So the ancillas start actually in the plus state. So it looks like this. Okay?
Can you correct for both? Like, we kind of have a thing here where we've got like some kind of, we start off with a single qubit.
Mm-hmm.
We have a really long channel. So the idea is
right.
we go 1 qubit to 3, pass it through this long channel, and do
right.
the code at the end. But I assume that like usually in this long channel, you can't tell what kind of axis your bit flip will occur on.
Well, okay. I mean, frequently you do know what kinds of errors occur in the channel. I mean, you know a lot about the channel. But it's certainly a possibility that you could have both bit flip and phase errors occurring with some probability. And these codes are kind of bad in that case, right? Because while this code is good at correcting bit flips, doesn't correct phase flips. This one corrects phase flips, but not bit flips. And moreover, actually, that code makes phase flips worse because there's now 3 qubits that the phase flip can occur on. And any one of them will ruin the phase. And similarly, a bit flip on any of these 3 qubits will ruin it. So, so these codes are doing a trade-off between bit flips and phase flips. Yeah?
So I'm not sure I understand what's the phase flip error. Is it just
yeah, okay, sorry.
Taking out an phase?
So yeah, so right now I'm just focusing on some simple errors. And so they're going to be the Pauli's. So we have X, sorry, yeah, 0, 1, 1, 0, bit flip, and Z, which is 1, minus 1. Yeah, so that's an example of a phase flip error, right? It's flipping the phase from, well, plus 1 to minus 1, for instance. Okay?
An arbitrary phase would be like condition 4?
Yeah, that's right. Right. Okay, so can we get a code that corrects both bit flip errors and phase flip errors at the same time? And we can, and the trick is to combine both of these codes and use extra qubits. So for instance, here's the 9-qubit code. So the 9-qubit code, we're taking a 0 and encoding it as 3 copies of 0, 0, 0 plus 1, 1, 1. Okay, now I'm regretting writing this out, but. Okay. And of course, if you have a superposition, alpha 0 plus beta 1, well, we're going to do alpha of all of this plus beta of all of this in order not to violate the no-cloning theorem. Okay? And so this code, I claim, corrects both bit flip errors and phase flip errors. So if we have a bit flip error somewhere, well, we can look within each set of 3. We can do that circuit over there to see, are the first 2 qubits the same or different, or the second 2 qubits within this set of 3 same or different. Then we can identify if one of them has been flipped. Okay? And similarly, for phase flips, well, what we want to do is we want to compare the phases. Right? We say, are the first and second phases the same or different? And are the second and third phases the same or different? Okay? And that's slightly more involved. It involves more qubits. But it's the same basic idea. Okay? We can compare the phases without finding out what the actual phase is and therefore learning about the encoded state. Okay? So this is a code that corrects both X errors and Z errors. And actually, it also corrects the Y error. Which is both a bit flip and a phase flip simultaneously, along with a global phase. It doesn't really matter. And that's because kind of the bit flip part and the phase flip part are basically independent for this code. And so actually, this code corrects both a bit flip, not just a bit flip or a phase flip, but a bit flip and a phase flip simultaneously. Both happen. Even if they're on different qubits, it corrects them. The Y is the case where they're on the same qubit. Okay. So anyway, so this is a code that that corrects bit flip and phase flip. So that solves our problem 3 up here. Okay? So question, yeah?
So you're saying that this would correct for 2 errors then?
Some cases of 2 errors, right? So there's actually a lot of cases of 2 errors it can correct. It can correct for a bit flip and a phase flip, even if they're on separate qubits. It can correct if you have a bit flip on, say, the first set of 3 and another bit flip on the second set of 3. It can correct that as well. But suppose you have 2 bit flips on the first set of 3, right? Well, it won't correct that. And what will happen? Well, so we'll have, for the 0, we'll have 1, 1, 0 plus 0, 0, 1. And it'll correct that back to 1, 1, 1 plus 0, 0, 0, which is the same thing. So 0 doesn't get changed. But the logical 1, we get 1, 1, 0 minus 0, 0, 1, which gets corrected to 1, 1, 1 minus 0, 0, 0, which is an overall minus sign. So it does a logical phase flip in this case.
But wouldn't that then get corrected?
No, because see, it's still 3 minuses here by comparing the phases. So it doesn't know about that. Okay, so that's an example of a 2-qubit error that's definitely not correctable by this code. So it corrects some 2-qubit errors, but not all of them. Yeah.
Classically, we can correct for n errors by like having like 2n plus 1.
Mm-hmm.
Right? Can you do something similar quantum mechanically?
Sure.
Just like have more of those?
Yeah. So if we want to generalize this code, we're going to need 2n plus 1 squared, right? Because we have kind of the inner layer that's a repetition code for bit flips. That uses 2n plus 1. And the outer layer, we need 2n plus 1 copies of those to have the phases to compare to. Now you can do better than that. And this 9-qubit code is also definitely not the best thing you can do to correct both a bit flip and a phase flip. But it's conceptually simple. Other questions? OK. So then let's move on to problem 4. And so now maybe you might be getting a little bit worried, right? Because in order to go from correcting just bit flip errors to both bit flip and phase errors, I have to go from 3 qubits to 9 qubits. Okay? And now I have an infinite set of errors that I want to correct. So does that mean I'm going to need to add more qubits and infinitely many qubits? That would be kind of bad. But instead, let me do something that's really quite naive and actually seems kind of stupid, which is suppose I have one of these more general errors. And let's take a very specific example in a moment. And then I'm just going to try to pretend that it's just a Pauli error. And just go ahead and deal with the code in the normal way and not worry about the fact that it's this more general error and see what happens. OK, so what specific error do I want to use in an example? Well, I'm going to use this R theta. Other page. And actually, let me use R2 theta for a reason that will become apparent in a moment. So we defined that in the first week. E to the I2 theta. OK, which of course you can take out a factor of e to the I theta. And we get e to the minus I theta, e to the plus I theta. It's a much nicer version to use here. And that's up to this phase factor. Well, we can expand this as cosine theta plus I sine theta, or minus I sine theta, cosine theta plus I sine theta. And what do we get? Well, we get cosine theta times the identity minus I sine theta times z. Okay? And then when we suppose we have this error occurring on a code word, so we have R2 theta on, I don't know, the jth qubit, and we apply it to a code word psi. Well, then we can write out this expansion. And we're also going to have some ancilla qubits that we're using to measure the error synchrome. So what do we have? We have cosine theta times I psi, which is just psi, minus I sine theta times z on the jth qubit applied to psi. And then the ancilla is 0. Okay? And like I said, what I want to do is I want to take this thing and just treat it like it's a Pauli error. Okay? So we are going to interact this qubit with the ancilla. And the ancilla is then supposed to acquire information about that tells us the error synchrome, right? And so it's going to tell us what Pauli error occurred, if it were a Pauli error. So what does that process do? Well, so in the case where we just have psi 0 gets taken to psi, and then an error synchrome which says that there's no error, right? Which is probably the all zeros error synchrome. Okay, so if we had this thing, that's what would happen. Now, if we had this thing, what would we get? Well, we'd get, we have the phase error here, and the ancilla would tell us there's a phase error on the jth qubit. Okay? Now, the thing is that this procedure we're doing to measure this error synchrome, we haven't measured yet, but to interact with the ancilla, is a linear procedure, right? Because everything we do in quantum mechanics is linear. And so up here we have a superposition of these two possibilities. So what we'll get out at the end is a superposition of these two possibilities, right, with the same amplitudes. So in particular, we have this state. Cos theta times this minus I sine theta times this. Okay? And then we measure the ancilla to actually see what the error synchrome is. And so one of two things happens. Either we collapse on this. These two are distinguishable. So we're going to collapse on one of these two possibilities. And with probability cos squared theta, I guess I don't really need the absolute value. Probability cos squared theta, we get this. Psi, no error. And with probability sine squared theta, we get the second possibility, that there's a z error on qubit j, and the synchrome that we measure tells us that. Okay? So now notice something kind of miraculous has happened. That after we did this measurement, either we get this possibility where there's no error, and the state is actually the correct thing, and the synchrome tells us that, or we get that there's a z error on this state, and the synchrome tells us that. So this kind of stupid thing of saying, let's pretend it's a Pauli error, and then just treating it that way, has made it actually happen. Right? It's kind of a triumph of wishful thinking. And this is kind of the miraculous thing that makes quantum error correction work, that you have, by measuring the error as a Pauli error, you collapse it to actually be a Pauli error. Okay? And so we can generalize this statement here. And this is not just a property of the non-qubit code. This is true of any quantum error correcting code. So we have the statement that if a quantum error correcting code, so quantum error correcting code, QECC, corrects errors A and B. Then it also corrects the error alpha A plus beta B. Okay? And so in particular, so if a quantum error correcting code corrects I, X, Y, Z on single qubits, it corrects all single qubit errors. So why is that? Well, I, X, Y, and Z, so here's X, Y, and Z. The identity, of course, is just this. So that's 4 2x2 matrices. And they form a basis for the linear space of all 2x2 matrices. Okay? So in particular, for instance, we have some sort of unitary, arbitrary unitary on a single qubit, where we can write it as a sum of I, X, Y, and Z. And the code corrects that. So by this theorem and that argument, measuring the error syndrome will collapse into one of those things, and we'll be able to correct it as a Pauli error. Okay? And actually, it extends even beyond unitaries, because the most general thing we can have on a single qubit is a completely positive map. Okay? And a completely positive map, well, you can write the CP map in this way, right, with the Krauss operators. And these things don't have to be unitaries, but if they're acting on single qubit, they do have to be 2x2 matrices. Okay? And so we can still expand them in terms of I, X, Y, and Z. And so what is this saying, basically? This is saying that psi goes to AK psi with some probability over K. And we can correct this 2x2 matrix, so we'll get back the correct state. And we can do that for all of the AKs, because this thing only acts on a single qubit. Okay? And therefore, we'll always get back the correct state, no matter which of these possibilities occurred. Okay? So it really does correct all single qubit errors, including decoherence and anything else you can think of that acts on a single qubit. So this 9-qubit code, then, as an example, is really a true quantum error correcting code, because it corrects all single qubit errors. Okay, and I guess I can also tell you, we're not really going to go into this, but if you want to make a code that corrects more errors, well, then something similar happens. You can just correct tensor products of I, X, Y, and Z on T qubits. Then it corrects all T-qubit errors. And again, that's because the tensor products of I, X, Y, and Z on T qubits form a basis for the T qubit matrices, the 2 to the T by 2 to the T matrices. Okay? So any questions about this? Yeah.
What is the complexity of this protocol?
The complexity.
Quadratic?
Well, so I haven't shown you anything scaling really. The 9-qubit code is just a fixed code, so it's a constant. If you think of the kind of generalized repetition code of 2t plus 1 squared, then it's kind of quadratic, I guess, in T. I mean, it depends which aspect of it you're asking about, but.
Like here, you're talking about making a tensor product to correct for like arbitrary multiple qubit errors.
Right.
So that scales with the number of qubits.
Yeah, I mean, so the number of tensor products of I, X, Y, and Z is exponential, right? Because I mean, there's, you know, if you have n qubits, and each of them could be I, X, Y, or Z, that's 4 to the n possibilities. Okay, but I mean, it depends. Again, it depends what aspect you're asking about. You only get one of them at a time, presumably. I mean, you might have a superposition, but when you measure the error syndrome, it'll collapse and it'll only be one of them. I mean, there's a lot of good statements that one can make and questions that one can ask about complexity in error correcting codes. We're maybe not ready to go into that in detail yet. Okay, other questions on this, though? Okay, so maybe this is a good time to abandon this focus on t-qubit errors for the moment, just very briefly to make a point. And suppose, I mean, so there's kind of two ways that the error rate can be low in quantum mechanics. So one of them is to say, well, there's a low probability of errors. And that's the argument I gave at the beginning. And therefore, only a few qubits with high probability, only a few qubits will actually have errors on them. And the rest of them will be fine. But you can also say, well, suppose there's a small error, like a small rotation on every qubit. Okay, that's also kind of a small error. But it's also treated kind of the same way. So suppose we have the tensor product of some small u epsilon, right? So that's the error. So u epsilon is going to be, well, let me do that on the other line. It's not in the way. It's going to be 1 plus epsilon u prime, roughly. Okay, u prime is not unitary, of course. So it's something that's close to the identity. And so then we can expand this tensor product of n of these as a power series in epsilon, or I guess in this case just a polynomial in epsilon. And so we're getting the 0th order term is identity. And then there's an order epsilon term, which is u prime on the first qubit plus u prime on the second qubit plus u prime on the third qubit, and so on. Sorry. There. And then, of course, there's a order epsilon squared term, which has errors on 2 qubits, and an order epsilon cubed term, which has errors on 3 qubits, and so on. But when epsilon is small, those things are probably going to be negligible. And this thing here is a sum of single qubit errors. And we already know that if we can correct, you know, A and B, so we can correct u prime 1 and u prime 2, we can correct the sum of A and B. So that applies even when these errors are on different qubits. Right? That wasn't part of the argument. It didn't care about that. So that means that a code that corrects one error will get rid of this order epsilon term. Get rid in the sense of giving the correct state out. So the error rate, if we apply this sort of error to a code that corrects one error, the logical error rate is order epsilon squared. Okay, so it's not required that we just have a probability of error on the low probability of errors. It's enough to have a low amplitude of error as well on the different qubits, and the code will still help. Okay? Yeah?
How would this work if, or would this work at all if u prime differed from the first, the second, the third qubit?
Yeah, that's, I mean,
Like
the same argument works, right?
Yeah.
It's just convenient to write it this way.
Yeah,
but
like those u prime 1, u prime 2, u prime 3, those don't all have to actually be equal.
that's right. Yeah, that's right. They could all be different. And it's exactly the same argument, right? You still expand it out. It looks like this. And you still get sums of errors that you can correct. So it still works. OK? Other questions? OK. So one thing you'll notice as a consequence of this is that, well, I mean, I've been focusing a lot on Pauli errors so far. And now we know why, because correcting Pauli errors is sufficient to correct general errors. But actually, tomorrow and I don't know, the last 10 minutes today, I'll be talking even more about Pauli errors because they play a crucial role in kind of a lot of the formalism of quantum error correcting codes. So let me introduce the Pauli group. And that's a group, I'll call it P sub n. Here, maybe make it script P sub n, which consists of tensor products of I, x, y, and z on n qubits, and they'll have global phase plus or minus 1 or plus or minus I. Okay? And because I want it to be a group, I need this global phase. So a group, remember, is closed under multiplication. So if I take the product of two tensor products of I, x, y, and z, I get another tensor product of I, x, y, and z with possibly some global phase funniness going on. Let's see, I get the I, you can see already, because I have y is I, x times z. So y times z inverse times x inverse, and z inverse and x inverse of themselves gives us that factor of I. And then we have the plus and minus 1 because, you know, the Paulis anti-commute with each other. So like xz is minus the identity. So what other properties does this? Yeah.
We're not keeping track of this global phase, are we?
No, we are keeping track of it. Sometimes. It depends what we're doing. But sometimes it actually is important. So what other properties does this Pauli group have? Well, so I already kind of mentioned that if you have something in the Pauli group, then it squares either the identity or minus the identity. So x, y, and z all square to the identity, but because we have this phase of I, like I times x will square to minus the identity. And then maybe the other main property of the Pauli group is that if you have two elements of the Pauli group, either they commute or they anti-commute. Okay, so on one qubit, of course, x, y, and z, they all anti-commute with each other. Though, of course, everything commutes with itself and commutes with identity. But if you have two qubits, this is kind of more non-trivial, because you can have non-trivial tensor products like x tensor x commutes with z tensor z, right? Because each x gets a minus sign as you move it past each z, but two minus signs is a plus sign. Okay, so you have kind of a non-trivial arrangement of some things that commute and some things that anti-commute. But those are the only possibilities, and that's a very useful property.
Do we know much about the structure of whether or not the commuting relationship?
Yes, actually, we know quite a lot about the structure. So if you ignore the phase, then, so as I said, this Pauli group has 4 to the n elements, right? But it's actually 4 to the n plus 1 because of the phase. But 4 to the n elements, and you can write each of them as a binary vector of length 2n, right? 2 to the 2n. And so kind of part of that is telling you where the x's are, and part of that is telling you where the z's are. If you have a y, you get both. And then this property does do two Paulis commute or anti-commute, which doesn't depend on the global phase. If you think of it in this binary vector notation, it turns out it's a symplectic inner product. So it's like a symplectic structure that you may have seen in classical mechanics. And so it's basically kind of a linear sort of thing when you think of it in this way. Is that roughly what you're asking? Yeah, okay. other questions about the Pauli group? OK, so let me end by giving you kind of a preview of what we're going to be doing tomorrow, which is going back to the 9-qubit code. So I kind of sloughed over a little bit this when I talked about it before, but I want to now ask the question of how do we measure the error syndrome for this 9-qubit code? Okay. So remember, what we want to do is we want to say, well, within each set of 3, let's say where the first 2 qubits are the same or different, and where the second and third qubits are the same or different. Now let me rephrase that in a more quantum mechanical language. So what's an equivalent question? Well, now that I've introduced this Pauli group, let's focus on the Paulis. And so in particular, the question is, are these 2 qubits the same or different? Is the same as asking, is the state a +1 or -1 eigenstate of Z tensor Z? OK? Do you see that? I mean, if they're the same, then we have either +1 squared or -1 squared here, 0, 0, or 1, 1. And if they're different, then we have 1 +1 and 1 -1. OK? And we want to do that for the first 2 qubits. We also want to do that for the second and third qubits, for the fourth and fifth, the fifth and sixth, the seventh and eighth, the eighth and ninth. OK? So there's these 6 operators. We want to measure the eigenvalues of them. Now we also want to tell whether the phases are the same or different. And this is the part that I slept over before. I guess I'm not going to go to complete detail now. But we can phrase that question in sort of the same way, but by thinking about X operators instead of Z operators, right? Because I told you the Hadamard is switching between X and Z and kind of switching their roles. So we want to compare whether these 2 phases are the same or different. So how do we do that? Well, if it's just one X on this first set of 3, that's not going to help. That's not going to take us anywhere. It's a totally different state. But if we do X, 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 we flip all 3 of these bits, then that will extract the sign, right? Because 0, 0, 0 plus 1, 1, 1 goes to itself. But 0, 0, 0 minus 1, 1, 1 gets the phase of -1. Okay? So if we do 6 X's, 1, 2, 3, 4, 5, 6, on the first 6 qubits, then for both of these code words that have the same plus and minus, we'll get eigenvalue +1. But if the plus and minus differ, if we have 1 plus and 1 minus, then we'll get a plus and a minus, and this will have eigenvalue -1. Yeah?
Why don't we just collapse this, like, figure out the Z's, collapse it down to 3 qubits, and then figure out the X's?
Sure. That's something definitely you could do in this scenario where you have perfect quantum computers. But there's a reason that I'm introducing it this way, which is going to lead into what we're going to talk about tomorrow. And of course, we want to also compare the second and third phases. So we do qubits 4 through 9, bit flips on those. And eigenvalue +1 says they're the same phase. Eigenvalue -1 says they're the opposite phase. So whether we do it the way you suggested or some other way, at the end of the day, what we're doing to figure out the error syndrome is we're measuring the eigenvalues of these 8 operators. Okay? Now, this is not necessarily a unique choice of operators, right? We could have, instead of saying, oh, let's see whether the first and second qubits are the same or different, we could have said, well, let's see whether the first and third qubits are the same or different. That would be operator ZIZ. We're measuring the eigenvalue of that. But ZIZ, that's just ZZI times IZZ. With tensors in here everywhere, of course. Right? So if we know the eigenvalue of these 2 things, we also know the eigenvalue of this. But we could substitute and replace this one with this one, for instance, if we wanted. And so indeed, what you can do is you can look at any product of these. And the eigenvalue of that is going to be well defined as well. So that's what we're going to do tomorrow. Is we're going to look at the set of all Paulis that are products of these things. And the code words should have eigenvalue +1 for those things, for these operators. But when there's errors, we might get eigenvalue -1 for some of them. OK, and so let me stop there. And then tomorrow we'll talk about kind of more general stabilizer codes beyond the 9-qubit code. OK? So, but questions on today? Yeah.
When you said we can view for any small error, even if it acts on all of them, you wrote U as.
Right. Yeah, that's hidden now.
I was a bit surprised by that. I'm not sure I understand, because I thought the way that the 9-qubit code was fixing the errors was by finding differences. Was by finding difference between, like, there's one different, all of them are 0 and one of them is
right.
1, or all of them are pluses, there's one minus.
Right.
But if there is something that acts equally on all of them, how can you identify?
Yeah. So again, look at the math. So if we have something that acts equally on all of them, then we can expand it this way as a sum of something that does a bit flip on the first one versus something that does a bit flip on the second one, something that does a bit flip on the third one, and so on. So at this point, it's still acting equally on all of them, right? It's still a superposition, equal superposition. But then when we measure, we're collapsing to one of these possibilities. So basically, it's an example of spontaneous symmetry breaking, to use a word which normally we don't bother with here, but it's applicable. That's what it is.
Just to clarify that, when you say acting on all of them here, we're talking about, like, if we're using the 9-qubit code, we're talking about using the 9-qubit code to encode any different qubits. So we've got like 9 and.
No. So there's 9 physical qubits. There's 1 logical qubit. Okay? And the point is that this operator here is symmetric. I mean, assuming that they're all the same, not the case where they're all different. But if they're all the same, then this is symmetric on those 9 physical qubits. But the code doesn't know how to correct errors on all 9 qubits at once. Luckily, this is a superposition of possibilities that are asymmetric and that only have errors on 1 qubit at a time, and that we can correct. See, so when you do that procedure up there, right, and you go through the error correction and you measure the error synchrome, you will only see, it'll tell you that there's an error on only 1 qubit. Okay, and which one is going to be totally random because they're equally likely because it's symmetric. But the collapse makes sure it is only on 1, even though originally it was an error on all of them.
What would be harder to correct would be like U1, tensor U2, tensor U3, tensor U4, all of them, but that's higher order.
That's right. That's right. Yeah. Yeah.
Thank you.
Okay. Other questions? Okay.